Hey, Mark.
Hey, Gabby.
Is Adam also going to be in this meeting today?
No, he's on holiday today, so
Oh, yeah, there's
we
a
won't see.
Independence Day in Poland.
I think so. Yeah, yeah. So not until next week.
Okay.
Gabby, how has it gone on Officinalis since yesterday? Are you getting good results?
So I'm now able to run. It took me some time to understand how this thing is working, and I should probably start using better system to remember what I've done because I was giving them name one, two, and then like Abel, Baker, Charlie, Dog, and so on. I have some idea of what I was running, but I really should start giving them proper naming.
For about 3 or 4 years, we've had an idea to create from CBT some kind of database schema for storing results and querying results from runs, but no one's had the time to actually implement it. So if you're looking for a Python project, a database project, uh, this is
No,
something that we've wanted to do, but no one has time to do.
no, I'm
And
definitely not a
next
Python
next
person. I can read
next
some
time we
code.
have next time we have a student we can use.
Yes, we've
Mark,
tried that.
so
Sorry, go
one
ahead.
small correction to my statement before. FIFO compaction makes no impact. It's not a FIFO compaction, but breaking, I had to before I had two changes done at once, and then I broke them and I tried it again because it made no sense to me. So separating the PG info and PG log into separate column families, that's have drastic impact on performance. Just moving the M, let me see. Yeah, just moving the M column to FIFO compaction seems to be making no difference.
Okay.
So the difference is, I'm not sure why by separating PG info and PG log seems to be the problem.
Sorting. I bet it's sorting in the mem table.
I'm talking about 20% decrease in IOPS. Pretty big.
Gabby, you should see if you can get either my wall clock profiler or Adam's wall clock profiler working, because that will tell you the difference very clearly.
Then another thing, the reason I even started all this thing is that I added statistics about RocksDB statistics, like compaction and flash events and so on and so forth. How do I get to see them? Do I need to add them to the script?
Where do you output them to?
No, I mean, it's you have to issue a command. You need to issue, what is this?
Oh,
Ceph daemon command.
I
But
think
by
you
the
said
end of
that
the
you
script,
also didn't you say you also logged them to the log, to the
I do.
OSD log?
I do.
What debugging level?
I don't remember. I can
Okay.
check it.
I would suggest. I mean, you can do it. You can do it that way. We don't have a monitoring plugin to do like arbitrary socket commands, but we should add one. That'd be very useful. But in the meantime, before we do that, just in your ceph.conf file in that directory, change it to whatever debugging level you need for your output, and then look in the OSD log. It should be included in the directory, the result directory.
Yeah, I mean, the log is not as good as the command line because the log is just going to show you what happened now. It's going to see you had this, and that. Just every event happening, you're going to see a log event saying we just starting flashing and so on. The command line is going to show you statistics collected, how long between every flash event, how long it took, how many object we had, and so on and so forth. So if possible,
So
I would really like to be able to run this command. But you're saying it's require modification to the code. It's not something
so
that.
look at the chat window. This monitoring Python class.
The link is wrong, I think.
No, there is a monitoring. It's a monitoring Python class.
Yeah, you need to implement a custom monitoring class for looking at your asap command. We have other ones for doing other monitoring, but we don't have one for specific arbitrary admin socket commands. But you could add one very easily.
But the Ceph daemon is running, so it's possible to issue a command and collect this information.
Absolutely, yes. Let's see. There should be one in here already that grabs the. If I remember correctly, I think we grabbed the highest latency operations. Or at least we used to.
I mean, I would basically like to issue the command before you stop the script. I want to collect this information. For example, when you say you think the difference is compaction events, the performance deviation, you say maybe because there was a compaction. So let's see. I can tell you when the compaction happened.
So this is a good one to look at as an example. This collect-L monitoring, you can see that it starts this collect-L process at the beginning of a benchmark, and then it stops at the end of the benchmark. Instead of running collect-L, you could, in a loop, call the admin socket command that dumps your data, write it out to a file, and then on stop, kill the loop, destroy the loop, and make a thread, right? You make a thread in there, a Python thread, and then have it do its thing, and then stop it at the end when you call stop, and then have it dump out the data into the result directory. That's how I would approach this.
Okay, I'll need you to help me with that. I mean, I see that
I'm not
doable, but I mean, when you show me this thing, I'm not going to be able to perform any of this.
I will warn you. I wrote CBT, but I'm not the best Python programmer.
I mean, being worse, I can read some Python if I really have to, but I never developed anything in Python.
I have a little bit of a love-hate relationship with it, to be honest.
Yeah, that's better than me. So maybe together, the combined power of us going to give us something. I think in any case, you want this kind of information. You do want to know how many compaction, how many flash events.
Well, we know compactions. We've got the compaction stats already. It's the flush events we don't have. That's useful.
Okay, so I do have it.
Yeah. Okay. I think if we do this, we should do it so there's an arbitrary admin socket command, and then maybe in the YAML file you can set what things you want to record. Maybe we can do it some way that's very configurable without changing the code.
I just need it to happen in the end, just before you close the OSD. I just want to issue the commands. I just need to be done once.
Oh, so the way that this works, the monitoring in CBT works, is that you can start something at the beginning of the benchmark, and then you can end something at the end of the benchmark. So it would allow you to collect some data over an interval during the benchmark, and then not during the other periods of time, if you wanted to.
Yeah, we could issue in the beginning. It's going to be empty in the beginning. I don't mind it, but the end is what's important.
Is it useful to be able to see that over time throughout the duration of the benchmark?
No, because I try to summarize the information. I collect the information, and in the end, I'm going to dump it all.
Okay. right now in the log file from the RocksDB statistics, we get the event logs, so we can see at what points in time compaction events happened. It might be nice to be able to do that same thing with flush.
So that thing you have in the log, I do issue a log event whenever we go to flush, compact, the mem table is being frozen, a new mem table is created, all these scenarios, I'm just sending an event to show you that this thing happened.
Okay.
But I need the end result, which gives me everything together.
Sure. Okay, we should get started. Oh, go ahead. Sorry.
Yeah, and I'm still cannot explain why breaking pglog and pginfo into separate column families is causing 20% IOPS degradation, because it was not a FIFO. Anyway.
Breaking it up is resulting in performance degradation.
Yes.
Not. Now that is interesting. I'll have to think about that one a little bit. Okay, in the meantime, let me get started on the PRs, and then we can come back to discussion.
Sure.
All right, guys. So, welcome. Looks like we've got folks from Core. That's good. Not a whole lot in PRs this week, but a little bit. There's ongoing work by Intel on their libRBD client-side cache implementation using specifically Optane drives, but I imagine it's somewhat generic. The most recent PR is using AIO write operations. This is just ongoing work in their write-back cache scheme. So Jason, I believe, is continuing to review that. I will add that in. Jason reviewed that PR. Hopefully we'll hear more about that. It sounds like this is actually interesting to some of our customers potentially. So good thing. I did not notice anything had closed this week. If anyone knows of things I missed, feel free to chime in, but I didn't see anything. Okay, moving on. Updated PRs this week. Adam got back to the folks that are working on dynamic levels for RocksDB. I think right now they're just trying to get to the point where Adam can see the same behavior that they are seeing in their testing. And they have produced a couple of additional test results for Adam. So potentially next week, once Adam's off holiday, we might see more. But for now, they're just trying to sync up and figure out how to show this in our lab. The other PR that was updated this week, Igor's optimization for PG removal. Numerous people have looked at that. Kifu looked at it. I think Miha, you've looked at that. Adam's looked at it. There was some test failures and additional reviews of the code. Since we don't have Adam, Miha, do you have any comments on that PR?
Yeah, I think when I looked at it, it looked good overall, and Adam's recent testing also proved that performance-wise we are doing good. I think there are some nits that were left by Adam for like in terms of code review. I think that needs to be addressed and a final run-through pathology maybe. But there's one more, I think, question or I saw a comment from Dan Vanderster from CERN about the delete sleep option. I think Igor's testing showed that changing the value of delete sleep hybrid, if I remember correctly, was helpful, and he suggested we don't do that. So I need to revisit that part again.
Sure. Adam seemed quite happy with at least this first half of the PR. Do you similarly concur, having looked at the code?
Yeah, agree. Absolutely. Yeah, I think the part one is going to give us a lot of benefit on its own. Part two needs more concerted testing and even reviews. I think it's more complicated than part one.
Okay.
Part one has like some clear wins that are obvious. I think we just didn't get to doing it.
Cool. All right. Well, that's all I had for updated and new PRs. I did not see anything had closed this week. Let's see. And we have a number of things in no movement category here. I think nothing real interesting. The only thing I'll say is that Adam and I are continuing to work on the memory management for caching and have kind of a very rough plan for trying to approach reducing fragmentation. Adam's doing the bulk of the work on it. So next week he might also have more results for us. But I think we've got a good plan for maybe how to try to tackle this without completely rewriting the entire OST. So we'll see. Maybe it will work, maybe it won't. Okay, so that's it for PRs. Anything I missed, guys? Okay, moving on. Sridhar, are you here?
Yes, Mark, I'm here.
Can you just briefly kind of repeat what you had said in the core meeting regarding the look at the sharded upward queue that you saw in your testing?
Yeah. So basically, what I have been doing so far is testing with changes that basically change the default number of shards to one shard, and then increase the number of threads to 16 to increase the parallelism. And when I did some baseline measurements and compared it against the default shards that for SSDs, which is 8 and through 2 threads per shard, I noticed a dip in the throughput on the client side, almost up to about 40%, 40-42%. So that got me thinking as to why that's happening, and I basically tried to investigate that. Like we spoke yesterday, I ran the profiler against the code with the default shards, and I just paste the output from the profiler in the chat window, where we can see that the bulk of the time is spent in the wait state, early in the almost 95% of the time, as you can see there.
Yeah.
So if you can extrapolate that to when we have a single shard with double the number of 16 threads, so you can kind of guess that this can very well be the cause of the latency that we are, or the reduced throughput that we are seeing when I run with one shard and 16 threads. So this is the basic observation I had, and I was trying to figure out ways to probably mitigate this.
So, Sridhar, it's very interesting that you mentioned that, because about a year ago I was looking into some different tests where I was seeing the sharded upward queue introducing significant overhead, just trying to deal with lock contention there. I don't know that that's always the case for us, but I think as we go forward, we're going to see it more and more. At the time, I was working actually on the up tracker and trying to improve lock contention there, and I started looking at various lockless schemes for queuing, and this particular lockless queue looked very, very interesting. It might be something to consider looking at.
Okay.
It'd be a big project replacing the sharded upward queue with something like this, but I think it would be worth experimenting with.
Sure. Yeah, it looks interesting. I can dig a bit deeper into this and see if we can adapt this for our purpose. Yeah, sure. I'll just go through this thing. Maybe this
Okay, cool.
Yeah, Sridhar, maybe it's worth summarizing your latest findings with the M-clock scheduler as well. That's what you've been testing in running performance tests on, right?
Yeah. So you want me to share those results that I have right now?
Yeah, sure. Let's. I don't think we've done this in this performance call, so it might be worth sharing with the group.
Sure. Let me pull up that spreadsheet.
Sorry, Mark, a question?
Yeah.
There is, if I remember correctly, there is a multi-consumer, concurrent queue in Foley, in how they call it, Facebook's open library, which is a very well maintained and working library. So if this is what we are looking for, it might be a good idea to take a look at Foley.
Absolutely. Anything that people are interested in, I think it'd be worth, taking a look at this. The sharded Upwork queue is kind of like the hub of everything, right? So whatever implementation there works best is probably going to be, at least on the classical OSD side, is kind of going to be it's worth spending some time on.
Okay. I think I can find the link. 1 second.
Okay, I'm about to share my screen with you guys. Are you guys able to see the spreadsheet on the screen?
Yep.
Okay. So this is basically a spreadsheet that captures results from running tests with the changes that I made for mClock with the default shards, and also running tests with the modified shards, so the single shard and 16 thread. So as you can see, initially we made some baseline measurements where the total max throughput is what is shown here, about 21,000 IOPS is what I was able to measure using a FIO on one of the inserter nodes. So basically, the recovery tests were executed by reducing the baseline to about 50%. So the client is rate limited to about 10,000 IOPS. So using that, I basically ran through a bunch of recovery tests with the weighted priority queue scheduler first, bunch of runs using that, and also ran the tests with the mClock scheduler by modifying the background recovery limit to a lower value, just to see if the quality of service settings are satisfied. So you can ignore this the first set of tests here. So as you can see, with weighted priority queue, we are getting a mean client latency of 5.4 milliseconds. But this is through the span of the test. If you consider only the phase where the recovery and the client ops were going on, you can see that the client is experiencing quite a huge latency of around 14.4 milliseconds. So the duration of the client IOs was around like 420 seconds, but the recoveries that you can see here on an average completed in about 236 seconds. But the rest of the time, since the recoveries are done, you will get a more optimistic value for the client latencies. But to compare accurately, the client latency during the recovery phase, which is around 14.4 milliseconds. But with the mClock scheduler enabled, and since we have around 8 shards, so I set a around 15 IOPS per shard. I reduced the recovery. The max recovery was measured to be around 1.6 gigabytes per second. So the thought was to reduce it by about 25%. That comes to roughly around 100 IOPS. So in order to get that many IOPS, I basically had to set around 15 IOPS per shard, and we have 8 shards. So as you can see here, that the first thing immediately that you can see here is the increase in the recovery times. Earlier it was completing in about 236 seconds. Now we can see with mClock schedule enabled, it takes quite a bit of time, around 1100 seconds. So which indicates mClock is definitely doing throttling of the recovery IOPS. And consequently, on the client side, we see much better latencies. This is through the duration of the test of around 420 seconds, and the recovery spans even beyond the duration of the client IOPS. So through the duration of recovery, we see consistently the client IOPS to be around only about 6.2 milliseconds compared to 14 with wait priority queue. And this graph here basically tells us the story of the percentiles. This specific, these bars that you see here, these are client percentiles during the full duration of the test. This is only with during the phase of recovery, which is, as you can see, 14.5 milliseconds. And with mClock, you can see an immediate improvement here. It's only about 6.2. So this clearly indicates that the mClock is able to honor the settings that we want to throttle the recovery IOPS, and thereby giving the client IOPS much better throughput and latency. And this
graph is amazing, by the way, Sridhar. I just want to tell you that's beautiful.
And I basically had some custom scripts written that's yet to be merged into CVT. So it will generate these kinds of graphs, wherein it'll basically grab the artifact from FIO and then generate these graphs. This is the since the client IOPS was like for 20 seconds, you can see the client profile, latency profile across that time. And there's also one more graph here showing the 99, the 95, 99, and the 99.5 percentile along with the average through the duration of the test. You can see that the average latency stays white, and the blue line basically indicates the average latency experienced through the course of the test.
That's just for the test with the DM clock, or is it? It's up kind of to this.
Yeah, this is only with DM clock scheduler. I just took a sample from one of the runs to compare it against weighted priority. If you come further below, you can see that. So initially, you can see a huge spike in the latency during the early power portion of the client I/O with weighted priority queue, and then it progressively dramatically comes down. And this captures only the latencies during the duration of the recovery IOPS, which is around 230 seconds. And this graph basically tells how much latency was being experienced during that phase, client latency.
Sorry, what was happening between 0 seconds and 30 seconds? Why was the latency so much higher at that point, but then dropped so far down?
Our thinking was during the initial phase, there are a lot of peering events also happening, in addition to a lot of other things. So I think those events are eating into the time here. At least that's what the logs indicate during the early portion of the test.
Okay.
Early portion of the recovery, yeah. Once those peering events die down, the latency on the clients, they dramatically improve.
Very interesting.
And this graph basically compares the bandwidth with weighted priority queue, quite high as you can see, recovery bandwidth. But here with mClock, it is reduced to about 255 megabytes. With 15, it's around slightly increased to around 300 megabytes per second. Correspondingly, the recovery times also dramatically increase as opposed to the weighted priority queue. So this is with the default shards. Any questions here before I skip to the results from the single shard with 16 threads? Okay, let's skip to. So similar exercise here, but only change is I changed the number of shards to 1 and number of threads for shard 16. Here we can see the corresponding weighted priority queue latency jump more than twice to about 30 milliseconds. But the time for recovery remains pretty much stagnant. So in this case, since there is only one shard, I set the recovery limit in clock to 100 IOPS per second. And so through the duration of the test, we see this latency, which is nearly 4 milliseconds, which is further improvement to when we compare it against the default 8 shards and 2 threads per shard. So again, doing the same comparison study, you can see that only during the recovery phase, this is the profile, and with the recovery limit set to 100, this is the profile with the mClock scheduler. And the latency profile looks something like this with mClock for one of the runs. So looks much better when compared to running with 8 shards and 2 threads per shard. And I think this graph just does the comparison of the percentile latencies. You can basically ignore this. This was just to get some understanding.
So this is a test looking at 1 shard and 16 threads, and the other one we looked at was 2 shards and 8 threads, right?
8 shards and 2 threads per shard.
Oh, other way around. Sorry. Okay.
Other way around. Yeah.
Okay. Do you have a comparison of those? Like any graphs showing the difference between those two?
So the only graphs I have right now is one of the graphs is related to the bandwidth, which is pretty much the same for weighted priority queue, but with mClock, it's pretty much stagnated. In this case, it was around 300. I'm not wrong. Yeah, it is around slightly higher, 345 MB. So Mark, what kind of comparison graphs were you?
I may be misunderstanding, but I was wondering, do you the first tab in your spreadsheet and the second tab in your spreadsheet? I think that's what we've been looking at as one and the other. Do you have any graphs that show the same data in those tabs but compared to each other?
No. So what I've done is just maybe I can mix these two, the results that I obtain here and this result. Maybe I can kind of merge these two to give a comparison study between the two configurations. I can do that, yeah.
Okay, that's just what I was wondering. It looks like in this case the latency is much lower, right?
Yes, dramatically lower. This is around 4 when compared to here it was around 6.2.
Yeah, exactly. Okay. And is throughput, what's the difference in throughput?
Throughput is where we are trying to investigate right now. In case of a single
Yes, much lower.
16 threads, much lower. So
Okay.
probably around 40% lower. So this is what we are trying to understand and how to mitigate this. Yeah, so that's where we are right now. We need to dig a bit deeper into how we can improve the baseline throughputs with this configuration. If this is the direction where we want to go.
Very interesting. Thank you for sharing all of that with us.
Yeah.
I'm excited to see what you discover.
Yeah. With the concurrent queues, let's see. Maybe we can improve that much more. Let's see. Yeah. So yeah, that's all I had.
All right. Well, thank you for sharing. Any questions from anyone?
No, I just wanted to say this is actually pretty great. I don't think we've done, dug so deep with this stuff. At least in my knowledge, I don't know we've done this. So it's pretty good that we are comparing baselines with WPQ and the DM clock-based scheduler. Because if we want to go towards the DM clock scheduler, we need to have enough data to prove that it is better in all scenarios, right? So I think this is awesome.
Absolutely.
Yeah.
This is Wild West territory. You're on new frontiers.
Yeah, but these tests are only with random write workloads. We need to run a bunch of other workloads maybe to prove that this schedule is better than the weighted priority queue. Quite a bit of testing to do.
All right. Well, looking forward to hearing more. Very, very interesting work. All right. So we've got about 18 minutes left here, according to my clock. Very briefly, I wanted to mention that a couple of folks had requested accounts on Officinalis, and it seemed to be a very good time to get developers on these machines. That's been kind of the long-term plan anyway. So this week, Gabby and Ronan are our first developers that are going to be starting to use it. If there's anyone else that needs really high-performance machines, these nodes have no hard drives, NVMe and Optane only, lots of RAM, lots of cores. If you have testing that you feel like would benefit from these, let me know. We can probably get you set up on one. Otherwise, we also have inserter nodes that have hard drives and NVMe drives. They're a little smaller and a little slower, but they're still actually quite good for performance testing. So, let me know if that is either of those are resources that you'd be interested in, and we can try to get you hooked up. Beyond that, the only other thing I had on my list was on the RGW side, there has been discussion recently about file access to objects and what that interface looks like and whether or not it might be useful in different scenarios. So there has been recently some ongoing discussion with the folks that work on the IO500 benchmark. They have a benchmark called MD Workbench that tests object-based interface performance, and they're working towards harmonizing that with IOR and MD tests, which are classical distributed file system benchmarks, so that you can kind of test all of this using the same tools. They have asked us if we would like to participate as being kind of the initial test case for what they're working on. I don't know that anyone on our team has a lot of time to devote to this, but I'm hoping that we can possibly at least do some test runs for them. I'm not sure how much time I have to do it right now. Possibly Kyle Bader or possibly someone from Matt's team might be able to at least kind of see that it works. But anyway, we're working with them, and hopefully we'll be able to do some them to kind of showcase that their attempts to make a kind of a crossover benchmark like this actually works with an established open source distributed storage system like Ceph. So just wanted to pass that along. If anyone's interested in working on that, let me know, because everyone's very busy. Okay, that's all I've got. Would anyone like to jump in here in the last 15 minutes with any topics? Gabby, I see you're talking, but you're muted, I think.
Yeah, sorry. Yeah, so last time we mentioned the KV sync threads. And I think we need to better understand the role and if there might be the bottleneck for our performance. So the assumptions, and again, it's just assumptions because we still have no validation for this, is that adding items, so KV sync threads are responsible for collecting all the requests for RocksDB put and delete and putting them inside RocksDB after they've been sent to the write-ahead log. And the reason we're using a single thread, it's because it's guarantee a perfect synchronization, and actually just this, I'm assuming. Now, if RocksDB operations are expensive, and again, I have no number, I'm just assuming that adding an item to RocksDB is going to be somewhat expensive for various reasons. One, all the operations are done log-free by design, which we might be able to actually, I don't know, I didn't find any option to say skip synchronizations, but so the assumption there is everything is done using atomic operation, right? So using the built-in, like compare and swap and atomic increment and such. Those operations are very expensive. So this is the first thing. Second thing, we're using skip list, which giving us big O of log n operation, and I think there's a factor of 2.5 or something. So if you have many items, say you have hundreds of thousands of items, or say, make it easy. If you got 64K items, then you should be doing 16 compare operation per item that you insert. So again, that thing seems to be expensive. And also the keys that we use, that tends to be big. So I don't know about the compare, if the compare itself is going to be just expensive or just going to pollute L1 cache and such things. But it seems that it might be expensive to do all this compare. So the question is if a single thread is able to perform all this work without becoming a bottleneck, because until this thing happens, we cannot move forward. So if everybody else is waiting on this thread, then it's time we add another threads to help him out.
Yes, I agree, 100%.
Okay. So maybe next week, with help from Adam and Igor, I'll try and push just a trivial second thread, which probably is not going to follow the same semantic, we're not going to get the perfect serialization, but we might be able just to get a feeling if this is the bottleneck, because if this thing is not going to give us any impact, then it doesn't worth bothering with all serialization. If it gives us significant impact, then it's probably worth our time doing that.
Gabby, have you looked at this PR yet? The one that I just linked in the chat.
Just a second. Which one? Oh, even the one you just put.
Yeah.
Let me see.
This is from Majian Peng.
Maybe RocksDB pipeline, right? No, I don't think I've seen it before. Did you send it to me?
It was, I think, in a bigger email a little while back, but this is from Majian Peng.
Okay.
He did not see as much of an improvement with it as he was hoping, but I still think this is worth looking at.
Yeah, and actually I did, during this performance meeting, I did one quick test, which actually goes against my belief, my assumption. I tried to shrink the M table size from 256 megabyte to 16. So it's factor of 16, so log 4. So in theory, I should have seen 4 times less compare operations because of the way the skip list is built, right? If the size is going down by factor of 16, then the number of operations is going to go down by a factor of 4. But I didn't see any performance impact. I mean,
performance, I bet, was worse. Was it worse?
No, I didn't see. No, it's about the same.
Oh, okay.
So on the bright side, it might mean that we can afford to use this memory to do something else.
Look at the compaction statistics. See if you saw more write amplification. I suspect that you did.
No, I was using FIFO compaction.
Ah, okay. That might do it. In the case of traditional compaction, I bet you would see higher write amplification for compaction. That's what we used to see.
Yeah, so I'm thinking, so the one thing which sticks out, it almost seems as if the number of compare operation is not slowing down the KV thread. I was expecting the KV sync threads to get now more power because it's doing less compare operations. But it doesn't seem to do them any good.
Need to run a wall clock profiler.
KV sync thread is not a bottleneck.
I don't know if I believe that.
It's not one-to-one.
Yeah.
I mean,
we need to see wall clock profiling, I think. We need to understand what in your test case is taking time.
Yeah, okay. I mean, yeah, maybe with wall clock time, we be able to see that the time shifted to somewhere else. Maybe we're going to see somebody else is wasting time.
Could be. The fact that we see such a big gain when OMAP for pglog is disabled still makes me think it's KV thread though. KV sync thread.
It stands to reason, but this test was really going against this assumption. I cut the work for the KV sync thread by a factor of 4. And I didn't get anything. Sorry, I mean I did it only for the M tables. Oh, forgot. The pglog are going to the default table, not to the M table, right?
Correct.
Okay. My bad. So I was messing with the wrong column family.
Okay.
change the aim instead of the default. Just remember that it was a default. So you know what?
Yeah.
I'm going to repeat this test.
Okay.
So it also means the FIFO compaction I was using, it was done on the M table.
Okay.
Okay, so I should go back and change everything. Okay, I'm going to try to do this on my system where I can check things. And then if once I'm feeling comfortable about it, I'm going to try it again on this performance analysis. So I need your help doing a few things. How to run the clock, sorry, the wall clock timer. And
You can
B, how
try.
to,
You could try using mine, but it's been having problems recently, which is one of the reasons we're looking at using Atoms instead. His is harder to
okay,
get
so
going, but
no, in that case, I'm going to hassle Adam next week. He's working in my time zone, so it's easy to get him.
yeah, his is I think going to be faster as well, which is really nice. If you want to try to use mine today, I can provide
No.
assistance, but
I actually
this is
prefer to. No, I prefer to use his. Just because he's working in the same time zone like me, it just make it easier.
yeah, sure, I get it.
Yeah. So I need to do that, and I need to be able to find. I don't know. Do you think Adam might be able to help me to use the Python script to change it?
Maybe. I mean, I don't actually know how much Python programming Adam does. Kifu and Radek were both modifying some of the CPT code for Crimson, so they can also probably provide some assistance. I can potentially as well. But really, all you really need to do, even temporarily, you don't even have to modify CPT, right? You could just have a script that you execute, a bash script that just calls the admin socket command and dumps it out to a log file. I mean, you could do it during the middle of the benchmark, right?
Yeah. We see. So I got these two things. So I'm going back, and I will try to see what impact does the FIFO compaction. So what do we put on the M table? It's the OMAP, which your test doesn't use at all.
Yeah, let me look at the
M is
code
for
again.
the,
That
the,
sounds
the M.
right.
The M column family is the OMAP, which your test doesn't use at all. So whatever I do there doesn't make a difference.
Yeah, that would be very little, if anything, with RBD tests. You'd see a lot if you were running like HSBench with RGW tests, but not with RBD.
Okay. Okay. So I need to go back and modify the default table and see how this thing is done.
Also, you could use Adam's PR that actually puts pglog in its own column family. That might even be more clear, right?
Yeah, I tried it, and that was the one which gave me really bad performance. So I don't know. I'm going to try it also. Yeah, I was thinking about it. Maybe the bad performance is because FIFO compaction is really bad for us. So the first
It
thing
could be.
I'll try just to separate them using his changes, just to separate without making any changes. Just a column family split, and then I will see if it make any performance difference. If it
Yeah.
doesn't, then I will probably blame it on the FIFO compaction.
Hard. Every time we deviate from this standard behavior in RocksDB and start using things that are more exotic, we start running into issues. And, FIFO compaction should be really easy, right? But it's not very commonly used.
Yeah, if it's not maintained, it might be rotten underneath.
We might be able to make it better if we want to take it on. I mean, we could fix it if there are problems.
Okay.
If we want to do that.
Before the FIFO, yeah, so I'll try it and see if it make a difference, and I'll also try again shrinking the mem table size just for the default table.
Yeah.
The PG info, do we ever read it?
I mean, absolutely, you'll read it at some point. The question is when we read it.
No, I mean, do you read it for recovery or do you read it online?
Absolutely, we read it for recovery, right? But do we read it
No, I'm talking
online?
about recovery.
Yeah,
I'm
yeah,
talking like outside of recovery. Because
yeah,
shrinking the mem table is going to make it less likely to be found in memory.
yeah, exactly.
But if we
I think
never
you're
read
gonna
it,
have
so
to.
my understanding is that the PG log we never read, just for recovery.
Yeah, only for recovery because we keep our own in-memory copy,
Yes.
which
And the
itself is a
PG info,
problem.
yeah, it's another problem. But what about the PG info? Do we ever read them?
I think you'll be the one to tell us.
Um, I mean, we should know. I can check it, but we should know if we. Yeah, actually, I can probably start collecting stat counters for how many read accesses for this table.
Yeah. I want to say no, but I don't know for sure. So if there are any weird cases where we might. So I think you, unless Niha, oh, well, okay, she's gonna drop. I was gonna say, unless Niha or Josh can tell us for sure, this is not the area of code that I'm the most familiar with. So you might
Okay.
become the new expert.
Yay. Okay, so thanks.
Yep. All right, we're out of time, guys. Anything else? All right. Have a great week, everyone. Thank you.
Yeah, good night. I mean, good weekend.
Yeah, sounds good.
Bye.
See
See
you
you
guys.
later, guys. Bye.
Bye.